Okay, Nicholas, this is question number 2, right down here. Finding the line of intersection between two planes when you do not have a point on that line. So, finding the line of intersection between two planes, and one key thing is if you're going to use cross product, you have to do the minus the j value. That's one key thing. We'll get to that. First off, let's understand a little bit about planes. Here's two planes. Just as two lines only cross at one point, two planes only cross at one line. That's the only line where these two planes cross. It has a formula. The other thing about this line is it's parallel to both plane 1 and it's parallel to both plane 2. Now, when they give you these two planes like this, we can write down the plane value here of this one and the plane value of this one. Plane 1 and plane 2. Doesn't matter whether it's the brown or purple. But the normals are right in there. 4, 2, 6 is the normal for plane 1. And the normal is a directional vector that points perpendicular to plane 2. And the normal for this one is right there. It's 1, minus 1, 1. For this plane, it's the coefficients in front of x, y, and z. So that's normal 2 is also perpendicular to the plane it comes from, the purple plane. They're both perpendicular to the planes. Now what's interesting, if the line of intersection is parallel to the planes, the line of intersection is also perpendicular to these normals, which means if I find the cross product of these normals, it ends up being parallel to my line of intersection. In other words, it becomes a directional vector for my line of intersection. So if I find the cross product of these two normals, I will find essentially my line of intersection in terms of directional vectors. But the only trick is once I do the cross product, remember to do the minus j. That's one I think I was screwing up when I was doing the cross product. Well, let's find the cross product of these two normals. And first, let's find their normals. So again, normals are perpendicular that come from, this is the Cartesian equation for that plane. The normal is the units of that plane, and it is perpendicular to that plane. So let us find the normal 1 and normal 2. Now, the other thing about normals is they're directional vectors. So you can divide them if they have a number in common. So from plane 1, the normal 1 is the coefficients in terms of x, y, z. So let's do x, y, and z. The coefficients of the normal 1, plane 1, is 4, 2, 6. It doesn't matter if I divide it by 2 now. Those are all divisible by 2, and because they're a directional vector, I can divide them by 2. And the other one's the coefficients 1, minus 1, and 1. Now, I also want you to keep in mind the answer we got when we did elimination. The elimination one does not provide a point. It's using y as a reference point, and it's making x and y in reference to it. This one we will find a point, but let's first find the cross product. When I have a cross product in matrices, I should take my two directional vectors, and I'm going to find, like we did before, I'm going to eliminate x and find the cross product of y and z, and that'll give me my x directional. So 2 minus 6. So 2 minus 6 becomes 8. So that means my x, because I crossed the x out, is 8. Let's keep that in mind, 8. We'll just say 8x. Now the y, we cross out y, is 4 minus 6. It's minus 2. Minus 2. Now there's going to be a little trick here, because when we put it into here, we're actually going to change the sign. And we can change the sign if we want now. And for z, cross out z, I get minus 4, minus 2, minus 6. So z, I get minus 6. Notice I can divide all these by 2 as well, or I could have started with dividing this by 2. I might as well. It doesn't really matter, but I might as well. So that means I have a directional 4x. I also might as well change this sign right now. I have to take the negative of my y value, and my z value stays the same. So I have these. Now I'm going to divide them all by 2. 4, 1, and minus 3. Now, how does this compare to my original answers? Well, normal, remember, and I just put this up here. Remember that right here I had a 4t. Well, that's 4x would become 4t. And I have a t here, and I have a t there, and I have a minus 3t here, and I have a minus 3t here. So I might as well change them. I might as well just take the components. 8 comma, instead of 8 comma minus 2, we divided it all by 2. I got 4. Instead of minus 2, I made it the positive, so 1, and divided by 2. And 6 minus 6 divided by 2 is this. This is a directional vector, and it's going to be multiplied by an equation t. The only problem is we don't have a point on the graph. Now, my guess is your teacher was making x equal to 0 to find the 2 points, right? To find a point on the plane, we have to take the plane graph, not the, this is just a directional vector. We have to find a point on these planes. We also have to do elimination to make them match here. I don't know if he made you cross vector twice somehow to find it. But when we make x 0, so we're going to set x to 0 as one of our points. And it makes sense because the line intersection has to cross through x0 at some point. It's going through x, y, z, and it has to cross through x0 at one point. So we can just force to figure out y and z when x is equal to 0. So that means as a point of origin, I'm going to make my x 0, point of origin 0, comma. We need to find our y. When I substitute 0 into my equation for my planes, the x value goes away. The x value goes away. 4 times 0 is 0. x0 is this. And I'm left with this. The problem is I cannot, now I can figure out where these two things meet will be the same x and y value. I can make them meet, and they just have two coordinates, so I can come up with the exact value. The problem is using elimination, I can't solve them. Now you can use elimination and substitution. If he makes you cross product at this point, I mean, it's kind of crazy. I guess we could. It would be, let's see if it works with cross product. So the cross product for y would just be 6. And the cross product for z would just be minus 2. Let's just see if that works. But we're going to instead do elimination. Well, the only way I can eliminate is if these match. The other way you can do it is you can make z equal to something. You can make z equal to 5 minus plus y. And you can just substitute it up here. And it'll work as well. We can try both methods. But in order to eliminate, these y's must have the same coefficient. So I'm going to multiply everything in this second line by 2. So it's going to become minus 2y plus 2z minus 10 is equal to 0 on the second line. All I did, I didn't change the equation down below. I multiplied by 2, and because x is 0, it won't matter if I multiply it by 2. And I get this. Whoop. Well, now I can subtract them. Now I can subtract them. I can't subtract them because the coefficients are opposite between y. When the coefficients are opposite, I have to add them, and that'll make them disappear. So I get 0. When I add these two, I get 8z. So I can just ignore the 0. And when I add these two, minus 14 plus minus 10 is minus 24. Is equal to 0. And I can solve for z. Z is equal to 3. So that means when x is 0, z is 3. I just need to find y. Well, all I have to do is take any equation, and I can even take the original one and make it x is 0. But in this case, I can just take this one, and I can make z equal 3. So I get 2y. What happens when z is 3 here? I get 18 minus 14 is equal to 0. What's 18 minus 14? It's 4. I get 2y's plus 4 is equal to 0. I get 2y's equal to minus 4. Y is equal to minus 2. So I have forced to find the point. I forced myself to find a point. I forced x to equal 0, and I found the points minus, when x is 0, y must be minus 2, and z must be, what did I make z? 83. Z must be 3. So now I have a point of origin that I can use for my directional vectors. So I got to go back to my directional vectors. As I remember, my directional vectors come from the cross product that I did for x, y, and z, which I believe I kept it around somewhere, but it doesn't matter. The cross products that I came up with were 4x, right? 1y, and minus 3 z. But I can also think of those as a point x, y, z, and I can just make that t, and I can use these individual ones. So I get this formula. X is equal to 0 plus 4t instead of 4x. Y is equal to the minus 2 I found plus t instead of 1y. And z is equal to the 3 I found minus 3t. So all I did was replace the t here for all these values. And it makes sense because this is a directional when you found the cross product and you found the parallel line, it was a directional vector, not a, it just had scale. So you had to find the original points and combine it. So there you go. That's how you find the point of line there. And we found this specific point, but we can find any point. And you can even find 2 points and find the directional vector. But if we broke it down into directional vector, it would be x, y, z is equal to our point of origin, 0, 0, 0, minus 2, and 3, plus t times our scalar that we found. The scalar we found was, I think, 4, 1, and minus 3, which are just the cross product we found earlier. And that is written in vector format, and this other one is written in so that one is written in the scalar. So I got it mixed up. That one's written in the scalar projection, and that one's written in the vector. So that's to solve any, you can find any x value by substituting the same value for t over here. And you can prove this works. How do you prove this works? You take your original scales. Not only will the 0 point come out to it, but you can replace wherever you see x in 1. So let's do this. Let's put these over here. Okay. Wherever you see 4x, you can replace it with 0 plus 4t. So I see 4x. And instead of x, x is equal to 0 plus 4t. And then plus 2y. Well, y is equal to minus 2 plus t. And then for z, I got plus 6z in the first line. And 6z is equal to 3 minus 3t. Now, then a minus 14 is equal to 0. If I have the right thing, all this left side should match the right side. So the left side should come out to 0. So 4 times 0, 0, I get 16t. Plus 2 times minus 2, minus 4. Come on. Plus 2 times t, plus 2t. Plus 6 times 3, 18. Plus 6 times minus 3, minus 18t. Minus 14. Add them all up. I get 16t plus 2t is 18t. I can see that it's 18t here minus 18t here. So those disappear. And I can see minus 4. Minus 4. There's an extra plus there. Minus 4 plus 18 minus 14 is also 0. So I can see on that scalar, that point is indeed, or that directional vector, or it's not a directional vector anymore, it's now a vector, is on there. These are 3 vectors. Now I can use the other plane, minus z, minus y, plus z, minus 5 is equal to 0. And where I see x, I can put in its equivalent, 0. Holy cow, 0 plus 4t. Where I see y, I have to put a minus 1 in front of it. Where I see y, I can put 2 minus 2 plus t. And where I see z plus z, I can put 3 minus 3t. And minus 5 is equal to 0. Now again, all my left side should match my right side 0. So this is 4t. Minus 1 times minus 2 is plus 2. Minus 1 times t is minus t. Plus 3 minus 3t. If I look at my numbers, oh yeah, don't forget minus 5. If I look at my numbers, I got plus 2, plus 3, minus 5, so the numbers all eliminate. And if I look at my t's, I get 4t minus t minus 3t, all that is 0 as well. So it's the right side. So for those 2 vectors, they fit into both those planes, which tells me that's the line. That's proof that I got the correct line of intercept. I hope that makes sense. I don't know if your teacher is then finding a scalar to find the points. When I did the cross multiplication of what was left, right, when I made x is equal to 0 here, let's see if I can find the points again. With this is just an experiment, so just ignore this part. So that's the result in the bottom left. When x is 0, I get this. I'm just seeing if I can do the cross product here. So the cross product of y is just 6, and the cross product of z is that a plus 2 or minus 2? Plus 2. Minus 2. And no, it doesn't work out, because that's a 6 and minus and plus 2. Minus 2. So the minus 2 matched, but the 6 didn't. So no, you can't do a cross product. If you can, let me know. I think you'd have to make both of them match, maybe something like that. And even then, it wouldn't work because you have to solve for a number. This number is relevant to it. So yeah, just do elimination. If your teacher wants you to do a different method after that, let me know. But that's the method I know that works. Long, 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 lots of mistakes. Why not just eliminate using the existing x, y, and z? Instead, you're going through an endless hell, in my opinion. And while this is good if you understand what's going on, if you're just memorizing a formula, it's pointless. It's better to do elimination. That's why they teach elimination.